Okay, good evening. How are you? I just want one person to confirm if they can hear me and if they can also see the screen that I am presenting. Hello?
Yes, we can hear you.
Okay. So this is just a discussion. So I will start with the last question, then I'll go through number 2, then lastly, I'm not quite sure about number 1, so that one is very much open for discussion. But of particular concern, or let's just start with number 2, then we go to number 3. Okay, so number 2 is saying it's about sensitivity analysis. United Refineries Limited is considering investing in an oil refining machine which has an estimated life of 15 years. The equipment will be purchased locally from mine machines at a price of 150. So this one should be changed to 120. Okay, so let's just write something here, because if it is 150, it's going to give us a negative NPV, and the sensitivity analysis will not make sense. Okay, so the oil refining machine has the capacity of refining 15 liters per annum. The contribution per liter is expected to be $2.75. Specific fixed costs are estimated to be 18,000 per year, and United Refineries has a cost of capital of 50%. So number A, calculate the net present value of the project. So this will be our working sheet. So let's just write it to say question 2. Okay, so this is simple. Here let's have the time. Here let's have the details. Here let's have the cash flows. Here let's have the discount factors. Here let's have the present values. Okay, so this one will be we use this table to calculate the present values. So the first cash flow of course that will be made in year 0 will be the initial investment. So the initial investment is negative 120 because it's an outflow. The discount factor is always 1 because it's here 0. The present value will be multiplied by 1, so it's still 120,000. Then our second, because this is 15 years, we can't really go year by year to say year 1, year 2, year 3. We can just say, okay, so from year 1 to year 15, what type of cash flows are we going to get? Because these are annuities, they are like annuities. So we are saying from year 1 to year 15, we're going to earn a contribution of 15,000 liters multiplied by $2.50. So here let's write contribution. This one is going to be earned each and every year, so it's a form of an annuity. So we are going to say 15,000 multiplied by $2.75. So what is our present value discounting factor here? We can just use the let's use the tables. So this table, our discount rate is 15%, and it's for 15 years. So we are talking about this column and this column. So our present value factor or discount factor is 5.847. So we come here, we put 5.847. because it's an annuity. So we are going to say this one multiplied by this one. So the present value of our contribution is this one. So it's a positive because it's income. Then again, year 1 to year 15, we're going to incur those specific costs. And we are given that they are 18,000. The present value factor will not change, and the calculations will not change here. What changes is the sign because it's an outflow. Okay, so now we are going to say our present value is sum of this one. So our present value becomes 15,000.9. 15,900. Okay, so this is our requirement number one, saying calculate the net present value. And now calculate the sensitivity of your NPV to the initial investment. So this is very simple. We are going to say, okay, by how many percentage should we allow our initial investment to fall, or our annual contribution to fall? Initial investment, it will be actual to increase because it's a cost. It's a cost. Also, the fixed cost, by how many percentage should we allow it to increase before we start, before the project is undesirable. For contribution, we will be concerned about the 4. So for all this, for the cost number 1 and number 3, we are concerned about their increase, and for the contribution, because it's income, we are worried about their decrease. Okay, so it's very simple. Number 1, the formula just say that NPV divided by whatever base that we are testing. So now we are talking about initial investment. So here we are talking about the initial investment. So it's 15,000 divided by what is our initial investment? Our initial investment is 120,000. So we can only allow initial investment to increase by 13% before the project is undesirable. So this one will be a plus. So we are saying it's a plus. Let me write something here. It's a plus 13%. So we allow the initial investment, because it's a cost, to increase by 13% before the project is undesirable. So that is the sensitivity of our initial investment to the net present value. And then the second is annual contribution. So annual contribution, formula will not change. We are just going to say NPV divided by present value of total annual contribution, which is equal to this one divided by our present value is this one. So okay. So it's 7%, rounded to the nearest whole number. All right, so this one will be a negative. We only allow the contribution to decrease by 7% before we actually before the project is undesirable. So it will be a minus 7%. Then the last one is going to say, what about the fixed costs? So again, the formula will not change. It will just say our present value of our net present value divided by the what do we call this one? By the present value of the fixed cost. So it will be again 15%, but this one should be a plus 15% because it's a cost. So it should be plus 15% because it's a cost. Okay, so 15%. Okay, so these were just the calculations. Our requirement was to just calculate the sensitivity, but you can always put comment to say, like the comments that I was giving, and as an overall comment, you can see that which one is too sensitive to the which one is too sensitive of the three. So we can see that the one with the lowest percentage is sensitive. So our net present value is sensitive to changes in um, in uh, in the annual contribution than any other variable than initial investment or fixed costs. Because as you can see, fixed costs here have to actually increase by 15% before the project becomes undesirable. But the annual contribution, only a 7% decrease, the project will be undesirable. So that is how you can analyze it. Okay, then draw a diagram to illustrate the sensitivity of the project to the annual demand. One way you can do this, you can say, okay, so let's put annual demand here, annual demand here, then we put NPV here. Okay, so we can say, okay, what is the NPV if annual demand is 0? What is NPV if annual demand is 1,000? What if the annual demand is 2,000? What if the annual, so the way we can do it, let's jump 1,000. So we put 2,000 here, we put 4,000 here, we put 6,000 here, we put 8,000 here, we put 10,000 here, you put 12,000 here, we put 14,000, 16,000, 18,000, and then 12,000. Let's go. Let's end at 20,000. So what will be the net present value if annual demand is 0? So let's just use a formula. We are going to say minus 120,000, which is the initial investment. Then we add the contribution. Contribution will be the annual demand multiplied by 2.75, which is contribution per unit, multiplied by the present value for 15 years, which we saw from the annuity present value table to be 5.847. Then we should deduct what was it, 18,000, which is fixed costs, multiplied by again the present value of the annuity. So if we don't produce anything, this will be the net present value. So in that case, we can just drag the formula down like this. Okay, so if we now have this, we can just say insert. Where is it? Where is it? Let's put a line graph. This thing is old. Wait a minute, what is that? Okay, the package is old. What do I do here? What do I do here? Not bar graph. Okay. Hey, I don't know why it looks ugly. Okay, or maybe it's the way my table is looking. Let me try horizontal one, then NPV. So we said 0, then with 2,000, then with 4,000, then 6,000, then 8,000, then 10,000, then 12,000, then 14,000, then 16,000, then 18,000, then 20,000. So the NPV, let's just copy the formula here. And then what we want to replace is to take this one like this. Then we can just drag the formula like this. Then we can just okay, now try to insert again a graph. Is because of my Excel is old, so that's why it's not giving me the option to, but I'm sure. Yes, I can hear you.
Sorry, on the contribution on the formula, you forgot to multiply by the discount factor. That's why the table is not coming out.
Okay. Let's show the formulas. Let's show the formulas. Where is show formula?
Yeah.
Okay, so as you can see, I said minus 120 plus B20, which is our demand, multiplied by 2.75, multiplied by 5.847. So 5.847 is the discount factor, isn't it?
Okay.
Yeah, so it's there. It's because of when I was using my other computer, it was giving me the option to actually insert the graph, but I don't know why this old computer, it's old Microsoft Excel 2007. So that's why it's not giving me the option, but let me see the best thing to, okay, let's say other charts. Okay, or charts. We want a line chart line. Ha, the lines that are coming out here. Hey. Okay. What are these? Okay, don't worry. If you have a proper Excel, it should come out. It's just because mine is not. Let me show you how it was. Let me see. I don't know why it's not coming out today, but it should be fine if you have a proper laptop. Mine is old. Mine is old. But you are getting the idea, isn't? That is the idea behind all this one. It's taking forever to open. Anyway, while it's opening, let's use your diagram to identify the minimum annual sales required to ensure that the project at least break even. I want it to be 14,009 units when I was doing these calculations. Let me see. Okay, let's not worry about that one. So, do we have questions on number 2? Do we have questions on number 2? We don't have questions. I'm not talking to myself. To learn, Brighton, do we have questions? Okay. Okay, that's fine. That's fine. Yeah, the graphs that are coming out here, they are just fun looking. Okay, so let's go to number 3. Linear programming one. So the trick on number 3 is coming out with the model. So here saying Central Beverages is planning of introducing a nutritious beverage, Super Sip, which will come in 3 flavors: orange, mango, banana. The management accountant is provided the relevant information about the products below. So we have ingredients, constituents, percentage makeup per ton. So we have emulsifiers, we have stabilizers, preservatives, and caramel. For orange, you have 10%, 10%, 20, 60, and all that. And saying input per ton, input prices per ton, we are saying emulsifiers, they are 150, stabilizers 60, preservatives 120, and caramel $10. Then maximum available pin tons per month. So we have these are our limitations. In most buyers we can only get 1,200. In the stabilizers we can only get 2,000. In preservative we can only get 2,200, and there's no limit for the caramel. The 3 flavors will be sold in bulk to local hospitals at a price shown below. So this is our selling price. Other variable manufacturing costs for each flavor, excluding the above materials, are 11 per ton. Required formulated linear programming model so that the company may maximize contribution and solve it using the Simplex method. Fully interpret your table U, your final table U. Okay, this is from Quab. Okay, so the first thing here, we want to maximize contribution, isn't it? So let's calculate contribution per unit for each product. So how many products we have? We have orange, we have mango, we have banana. Okay, so these are the products that we have. So we are going to say selling price, selling prices. These ones are given, so we do not have a problem there. We are just going to put 83, 81, and 81. Sure, those are the prices in tiers. The only direct materials. This is the one that should pose a problem. So how do we calculate these ones? We are told that the prices are 150 per ton. So for orange, obviously it will be 0.1 because it's only taking 10% of emulsifiers. So 0.1 multiplied by 120 because emulsifiers is costing multiplied by 150, not 120, multiplied by 150 because emulsifiers is costing 150. Then we say plus let me just put 10% here so that it shows what I'm doing. 150. Then plus again is 10% of what? Of stabilizers. Is it stabilizers? Yes, stabilizers. Then only 10% of 60. Then plus how many percentage? 20%. 20% of what are these? They are preservatives. So they are costing 120, 120, and finally plus 60% multiplied by 10. The final ingredient, or yes, the caramel. So if we press enter, we have 51 as our direct materials. We do the same thing for orange, mangoes, 10%, 10% of 150 plus what percentage? 20% of what? Of 60 plus how many percentage? 10%. 10% of 10% of 120 plus 60% of 10. So 45 here. Let's do the final one. How many percent do we have of 20, 10, 10, 60? So we have 20% of 150 plus 10% of 60 plus 10% of 120 plus 60% of 10. So that is our direct materials. Then we have this thing that they are saying other variable other variable conversion costs for each flavor excluding the above materials are $11 per ton. So other variable costs, we have 11. So our contribution, because contribution is equal to the selling price, less variables, we are going to say this one minus this one. So we are realizing contribution of 21, year 25, year 16. So this is our contribution. Because that's the one that we need to maximize, so we need to find contribution per unit. So this is the first thing that we have to calculate. So let's just call it working number one. We call it calculate contribution per unit. Then let's go to working number two. Yeah, you'll see the series of workings, but don't worry, it will be fine. So let's now formulate our linear programming model. Okay, so our linear programming model, we are going to say, all right, we are saying maximize Z. Z is equal to, so we're going to say 21. Let's just name oranges X1. Then we say plus 25. I'm just taking the contribution per unit. X2, which is representing mangoes, then plus 16 X3. Subject to, we are subjecting to these two constraints, isn't it? What constraint do we have here? So the first constraint that we have here, it will be, we are told that we have these our constraints. So we're going to say, okay, emulsifiers, we are going to say, okay, we need 0.1, which is 10%. For the oranges, which is X1, if we add it to, for the mangoes, it's again 0.1. Mangoes are represented by X2, then plus 0.2 X4. This should be smaller than or equal to, what units do we have here? It should be smaller than or equal to 1/200. Okay, so that is our first constraint. Then our second constraint, it will be for the preservatives. So it's 0.1 X1 plus 0.2 X2 plus 0.1 X4 is smaller than or equal to, how much is it? 2,000. We only have 2,000 stabilizers. Then number three, what is the percentage? What is it that we're dealing with here? Which is preservatives are also limited. So 0.2 X1, which represent oranges, plus 0.1 X2, which represents mangoes, plus 0.1 X, is it X, 0.1 X3. Which should be smaller than or equal to, what constraint do we have here? We have 200 to 200. Okay, so these are the only constraints that we have. As you see, the caramel we do not have a limit there. So we are going to say, so X1, so that we won't have negative outputs here. We're going to say X1 and X2, X3 should be greater than or equal to 0. So now we have our model. So once you have the model like this one, you can solve the linear program using the Simplex method. That was actually the most difficult part to come up with the model. Okay, so Let's go to working number 3 without delay. Working number three, we are going to come up with our, okay, working number 3, let's introduce select variables. Introduce select variables. So by select variables, we are saying, okay, because we want to maximize contribution here, we might see that in order to reach the maximum contribution, we might have some tons of mouse files that won't be used, or caramel or stabilizer that won't be used. So those ones are represented by the select variables. So what we do here, we are going to, on our, what do we call this one, when we say maximize contribution, whatever, this one we can express as this one. Let's move all these the things that are on the right side to the left, so that we leave 0 on the right side. So it will be what? It will be minus 21x1 minus 25x2 minus 16x3 plus z is equal to 0. So we've just moved things from the right side. What about, so we are also introducing second variable so that we convert our linear inequalities to solvable equalities. So what we do here, we are just going to copy these guys here, then you place them here. Then for this one, we are going to introduce one select variable. So let's just call the select variable x4. Okay, so we remove the smaller than sign, we are left with an equal sign. Then here, let's introduce select variable and let's call it x5. Then we remove the smaller than sign. Then this here, let's remove, let's again add the select variable, let's call it x6, and we remove the greater than, the smaller than sign. Okay, so we are also going to put limits here. Let's just copy this one as it is, you paste it here. Then here we are going to put the select variables x4, x5, and x6. Okay, so now we are good to go. Now, when we have now these solvable equalities, we can now go to our initial table U. Okay, so our initial table U, we are going to have x1 here, x2 here, x3 here, x4 here, x5 here, x6 here. We're going to have our z, and another last column, let's just call it b. Okay, you will see what b will be standing for, but you can call it anything. Okay, now on the x1, we are just going to take the coefficients on our first equation, this equation that I am highlighting in red. Let's just take the coefficient of x1 there, which is 0.1. Let me do some formatting here before I continue. Okay, so the coefficient of x2 on that same equation is again 0.1, then 0.2 for x3, then for x4 we have 1. x5 we do not have x5 on the first equation, so we just put 0. We again do not have the coefficient for x6, so put 0, and also we do not have the z. And our b, it represents the 1 to 100, the constraint. So b is the column for the constraints. Okay, we go to there. So that was the first equation. So let's just call equality. Okay, we do the same thing for the second equality. We're just taking the coefficients 0.2, 0.2, 0.1, 0.1. We do not have x4. We do have x5 and the coefficient is 1. We do not have x6. We do not have z. And our limitation is 2000. So that will be our second. Now, on our third, it will be, did I do the correct thing here? Let me revise this one. It's 0.1 actually here, then 0.2 here, then 0.1, then 0, then 1, then 0, then 0. Okay, then the last one, not the last one, 0.2, 0.2, then 0.1. I'm just taking the coefficient 0.1, 0.1. Then we do not have x4, we do not have x5, but we do have x6. Then we do not have z. The constraint is 200. That's our second equation. And then now we are on the bottom, we put our maximized contribution equation. So here on the x1, we are going to put the condition was minus 21, isn't? For mangoes, it was minus 25. For bananas, it was minus 16. Then we do not have anything here, anything here. Then we do not have anything here. Yes, we do not have anything here. No, the z was let me see the maximized contribution. We calculated it to be 0. Okay, so these are zeros. Okay, so this is our initial table U. When we have our initial table U, then we can go on and calculate and do our simplex calculations, and we interpret the final result. Okay, so our objective, we only have the optimal mix when we no longer have negatives in this column, in this row. As long as we still have a negative number on this row, then we have not yet reached the optimal mix. So the question is, how do we remove the negatives? So the first thing is to identify the pivot variable. So the pivot variable lies somewhere in the column where we have the smallest number in the last row. So the smallest number in the last row is 25, isn't it? Is 25. That is the smallest number in the last row. Okay. So it means that our pivot variable lies somewhere in this column. Okay, so this is our smallest number in the last row. So how do we now, because it could be 0.1, it could be 0.1, it could be anything there, but we don't know for sure which one exactly. Okay. I just want to check 0.1, 0.1, 0.1 here. Something is not right on our second equation. Our second equation, this one should be 0.2, 0.2. Okay, so let me check 0.1, 0.1, 0.2, 0.1, 0.2, 0.1, then 0.2, 0.1, 0.1. Then we have 1, 0, 0, we have 0, 1, we have these ones are okay. Then I just want to check our maximize equation. Do we have a z? Yes, a z does have a positive 1 coefficient, so we're supposed to put a 1 here. Good. So now we're good to go. Okay, so how do we identify the row with our pivot variable? We divide B by those numbers that are in the pivot column. So we find 12,000 here, we find 10,000 here, we find 22,000 here. Then we identify the smallest number. And our smallest number, as you can see, is 10,000. So where these two joins, the smallest here and the smallest here, that is our pivot variable. So let's indicate it by a yellow code. Okay, so after indicating it by yellow code, what is the next? So the first step we say identify pivot variable. Okay, so we've identified the pivot variable to be that is 0.2. Then our working number 5 will be to make the pivot variable a unit. So we should make the pivot variable a unit. So that is very simple, ladies and gentlemen. Let's just copy the table here. Okay. So what we want to achieve here, this column, this row with our pivot, we should make this 0.2, we should make it a unit. So what do we do? Let's erase everything there. So what do we do? Of course, we just have to divide 0.2 by 0.2, isn't it? So if we divide 0.2 by 0.2, that's how we make it a unit. So here, so that we hold everything constant, we should divide everything by 0.2. So what we can do is we can copy this one here, but then we are going to fix our 0.2 because we are going to divide everything by 0.2. So let's fix this one. Okay. Okay, so we are saying this one divided by 0.2. Okay, so 0.2. So let's fix 0. Okay, so everything should be divided by 0.2. So if we drag our formula here, dividing everything by 0.2, our objective was to make this pivot variable a unit. So now we can't just divide only the pivot variable by 0.2 and then we leave everything else. No, we have to divide everything else by 0.2. Okay. All right. So now we are good to go. So after making the pivot variable a unit, everything else or every variable in the pivot column should be made 0. So all these ones that I'm indicating in green, we should make them zeros. How do we do that? Of course, it will be simple. Let's just copy. So let's name it working number 6, and we say make all other variables in the pivot column zeros. Let me put it like this. So we want to make everything else a 0. All right. And how do we do that? I just want to confirm if you are following me or I am talking to myself. Anyone, Brighton, to learn? I'm used to those two names. Do I still have people? Or we are not dozing? Okay. Okay. So the second objective is to make all other variables in the pivot column zeros. I'm talking about the other variables that are indicated in green. So if we let's just paste as paste special, and I want to paste as values here. Okay, I want to copy this one here. So what we want to do is to make these columns. We want to make them this column is okay because we worked it on this working when we were making the pivot variable unit. So the other columns, especially the first column, we have to make this 0.1 to become 0. So what do we do if we want to make 0.1 to become 0? Of course, we have to say is equal to the 0.1 itself, then we should minus 0.1 multiplied by 1, which is the pivot variable that was converted to be a unit. So as you can see now, we have a 0 here. So here we can just copy the formula. That is no harm. We can just copy the formula. Okay, so that is it, ladies and gentlemen. We can do it for the third column. Third column, in order to make this 0.1 a 0, we have to say is equal to that 0.1 minus 0.1 multiplied by the one that is multiplied by the pivot column. So as you can see, we have a 0 here, and we can just copy it like this, and we are there. Then lastly, in order to make this minus 25 a 0, what do we do? Of course, we have to say minus 25. Then we say plus 25 multiplied by the pivot row. Okay, now we have a 0. Yeah, what happened here? Then we can copy the formulas to the other cells. Okay, voila, that's where we are now. So that is a new table U. So we call this one new table U. Okay, so our new table U looks like this one. So have we reached the optimal mix? No, because we still have negatives on our last column. As long as we have negatives on our last column, we have to repeat the process. So how do we repeat the process? Now we have to identify again the pivot variable. In this case, our smallest number in the last column is 850. And how do we find the pivot row? We check by doing this. How do we check? We say B, which is our constraint, we divide by the pivot column. So this is how we check. So the smallest here will be which one? So the smallest actually is the first one. That is our smallest. So that means our pivot variable becomes this one, where it is intersecting. So I'm not going to repeat the process step by step here. I am just going to put things here. I'm just going to formulate again a new table U, but the procedure is that the same. We have to make the what do we call it? We have to make the pivot variable a unit, and after making it a unit, all other variables in the pivot column should be zeros. So now we are going to have only the final table U here. So in order to make the pivot variable unit, is this one, isn't? We should divide it by 0.05 so that we make it a unit. As you can see, it's now a unit. Then we drag the formula up to the end. Okay, so let me just remove the yellow coding because it only I should only refer to this one. Okay, so what do we do to the next column to make these ones that are indicated in green, to make them zeros? What do we do? Of course, for the second one, we are going to say the column itself minus 0.5 multiplied by the pivot row. So as you can see, now it's 0, and then we can copy the formula throughout. What about the second one? To make 0.0515 0, we will say the 0.05 itself minus 0.15 multiplied by the pivot row. And then we now have a 0. Then we drag it to the end. Good. Then lastly, we are going to say to make minus 8.5 a 0, what do? We say minus 8.5 itself, then we should add 8.5, then multiply by the pivot column. And now we have a 0, and we drag until the end. Voila! Now we have the optimal solution. Because as you can see, we no longer have a negative on our last row. Let me just indicate the last row in green and bold. As you can see, here we have 0, 0, here we have 22, here we have 170. We no longer have a negative here. So as long as we no longer have a negative on the last row, then we have reached the optimal solution. So the question is, how do you interpret this? All right, so you saw the calculations, but how do you interpret? So it means, so for x1, it means we should produce x1. X1, we said it was representing oranges, isn't it? So that means we should produce oranges. How many units? 4,000 units. We are taking those units from B, from this column, B. So how do you know? As long as we have 0, 0, zeros on all the other variables and we have a 1, where in this case, this person is joining this time. Okay. So for x2, because we have zeros and a 1, it means that, what was this? It was bananas? No, mango. Okay, it means we have to produce 8,000 mangoes. What about x3? As you can see, x3, it was representing what, by the way? It was representing bananas. We actually have to produce 0 units because we still have these figures. They should be at least zeros and a 1. Like what we have here on the first one, we have zeros, 0 here, 0 here, 0 here, and a 1. So we are going to trace the 1 up to column B. So that will be the units that we are going to produce. We did the same here. We traced the 1 up to column B and we said 8,000. Here, although we don't actually have a 1, we have a negative 1, and also we don't have zeros. We have 3, we have 20, we have 0.4. So the interpolation is for that particular variable, we put 0. The same applies to x4, we put 0. And x5, we put 0. x6, we put 600. Tons. x6 was representing what? It was representing, was it a multipliers or something? Preservatives. It was representing preservatives. So it means what? It means that because initially when I defined select variables, it was representing unused materials or unused tons of those ingredients. So that means the optimal contribution, which was represented by Z, is $284. Okay, so it means what? It means to the maximum contribution that we can ever get from these products is 284, and that maximum contribution is found by what? By producing 4,000 units oranges and 8,000 mangoes and 0,000 0,000 what? 0,000 of bananas, and we should have stock of 600 of unused emulsifiers. So if you just want to check, if we say 4,000 multiplied by the quantity that we get, it was 21 for oranges, and if we say plus 8,000 multiplied by the quantity that we get was 25 plus 0 multiplied by quantity that we get was 16, you could get your 24 to 84,000. That is the maximum quantity that we can ever get. So this is the interpretation. Okay, that is it, ladies and gentlemen. That's how you get your 25 marks on that question. So do we have questions? Or and long as people? Do you have questions, guys? Questions. The platform is now open for questions. This was the simplex method and the question number 3. If we don't have questions, that means the calculations were clear, or they were not clear, or you didn't understand anything. Those are the two possibilities, of which I think the latter is the correct one. Guys, am I talking to myself? Am I on mute?